Here you're given a problem with a lot of arithmetic happening to powers of, in fact, 3 different variables here. We've got some powers of u, we got some powers of v, we got some powers of w, and we have a lot of stuff going on. We're multiplying powers, we're dividing powers, we're taking powers of powers, we're grouping them with some parentheses, so there's a lot going on. And the ultimate goal of this problem is to simplify this expression completely so that ideally each one of the different variables is only written once. So we only have one collected power of u, one collected power of v, one collected power of w, and whatever constants that we have only appear in one place. So we want to get that as simplified as possible. And following the order of operations, as we talked about last time, gives us a framework for kind of setting an agenda of a step-by-step. So when you approached this problem, what was the first thing that you thought about trying to simplify? The first thing that we approach, first thing that we attack, are these parentheses. Again, it's kind of like following the order of operations, with distributive property being kind of how we handle the P in PEMDAS. Right? And so how it works, just in general for the distributive property, is that anytime I'm multiplying 2 things together, I'm just going to write x times y inside parentheses, raised to the power n, that power can distribute across the multiplication on the inside, so that we'll get x to the n times y to the n. And the same thing is also true with division, which is actually how we're using it in this problem. That if I have division inside of a quantity, and that quotient is all being raised to a power, that power also distributes across each of the factors in the division. So that this ends up being x to the n divided by y to the n. And that's where we begin on this problem, distributing this -3 into the numerator and into the denominator of this big fraction. But then when I do that, it turns out that my numerator also has several factors of its own, 3 times u to the 3rd times v, and that -3 therefore gets distributed to each of those. So that -3 power ends up in a lot of places after we do this distribution. Namely, we end up upstairs with 3 to the power -3 times u cubed to the power -3 times v to the power -3, and then downstairs we end up with w to the power -1 raised to the power -3. So that -3 shows up in 4 different places after we finish our distribution. And then we have this other factor that we're not doing anything with yet, u to the -4, w to the 5. And in fact, now these parentheses around the u to the -4, w to the 5, those aren't really necessary anymore. Because of the associative property of multiplication, we can just write them like this, times u to the -4 times w to the 5th. And so that gets rid of the big set of parentheses that we have here by distributing. And now we've taken care of the P in PEMDAS, in a sense. Following the PEMDAS philosophy, now that we've kind of done the distributive property to tackle our parentheses, let's next do something that can help us to tackle the exponents. And what I like to think of as tackling the exponents for us is this property that we talked about last time, which is how do we raise a power to a power. So if I have x to the power n, and I raise that power to another power, the mth power, how do I simplify that? What do I do with the 2 exponents, n and m, when I raise a power to a power? For example, u to the power 3 raised to the -3. What do I do with that 3 and that -3 to combine those exponents together when I raise a power to a power? Multiply. Yes, exactly. It's one step lower on the arithmetic layer cake than the operation that's happening to the power is the operation that's happening to their exponents. So when I raise a power to a power, those exponents multiply. And that'll be the next thing that we worry about in simplifying out this expression. And that's happening in 2 different places right now. It's happening in here, u to the 3rd raised to the -3, and it's also happening down here in the denominator, w to the -1 raised to the -3. So we'll do that step next. I'm just going to highlight those 2 places for us to use this property. And when I use it in those 2 places, how many u's do I get upstairs here? negative 9. 3 to the power negative 3 times u to the power negative 9 times v to the power negative 3. And downstairs, how many w's? 3. Positive 3, negative 1 times negative 3. Great. U to the minus 4, w to the minus, or w to the plus 5. Great. And now all of our parentheses are gone once we've finished with the power of a power business. Before we go on to the next step, what I actually want to do real quickly is just simplify this fraction multiplication that I have going on over here, right? This is a bit like one of those fraction problems where you have to multiply a whole number multiplied by a fraction, right? Because this quantity out here in the front looks kind of like a whole number. This quantity over here looks kind of like a fraction. So how do we turn a whole number into a fraction in order to multiply it with another one? Yeah, just put it over 1. Give it its own denominator, namely a denominator of 1. So I'll do that. And then when I multiply fractions, how do I multiply? Straight across the numerator, straight across the denominator. Right. And then that becomes the time where now I can see that I'm going to have powers of u that combine with one another in the numerator. And then I've also got some w's that are separated, some of them in the numerator, some of them in the denominator. So I'm actually going to take this opportunity to use the commutative property of multiplication to trade places between this v power and this u power, so I can get the u's next to one another, just so that it makes it a little easier for me to focus. So I'll have the u to the minus 9 followed by the u to the minus 4. And then I've got my v's, v to the minus 3, and then I've got w's, 5 of them. And then downstairs I have w to the third power times 1, which multiplication by 1 is an invisible operation, so I just won't write that. Okay? W to the third power. Okay, now that everything is together, now I see one opportunity to multiply powers. Highlight that one in orange right here. The u's can be multiplied. And then I also see here an opportunity to divide powers. And just for the sake of being especially brutal about it, what I'll do is I'll move that w to the third power, so I'll slide it over so it's underneath the other w's. So w to the fifth on top, w to the third on bottom. That just kind of reinforces that that's going to be an opportunity for us to divide. So now let's get our general principles down. If I multiply two powers of the same base, let's say I multiply x to the power n times x to the power m, now what arithmetic do I do with the exponents to combine them together into a single power? Right, there is our addition. So multiplying powers of the same base results in an addition of their exponents, n plus m. Meanwhile, of course, if that's what I do when I multiply powers, what do I do when I divide powers? Subtract. Right. The opposite of multiplication is division, and so the thing that happens to their exponents is the opposite of the thing that happens when we multiply powers. So instead of adding, we subtract. We get x to the n minus m. All right, so now we know what to do for each of these two examples. So we'll do it. The total number of powers of u that I have is going to be negative 9 plus negative 4. What's negative 9 plus negative 4 other than an opportunity to make a sign error? What is negative 9 plus negative 4? Negative 13. Those two numbers have the same sign. They're both negative. So when I add them together, it really is an addition problem. And it keeps the sign of the one with the larger value, but since they're both negative, it keeps the negative sign. U to the minus 13. Okay, so that's what happens to my u's. Now what happens with my w's? I have w to the fifth divided by w to the third, and so that's going to give me how many w's in total? 5 minus 3. 2. Right. And you'll notice now, by the way, that I've left the denominator of my fraction empty. We never want to do that. Just make a note to yourself when that happens, that an empty denominator, just like an empty numerator, means that there's a secret little 1 hanging out down there, right? For the same reason that we introduced this little 1 over here with this whole number quantity. So great. We've now done everything there is to do in the order of operations. We dealt with the parentheses. We simplified powers of powers to appease the exponents, and we simplified the products and the quotients of powers to deal with the m and the d. There's no addition or subtraction to speak of, and in fact there won't be until we move on to our next unit on polynomials. That's the one you're going to be reading about over the week. And so then the last thing that we haven't done yet is we haven't done this second part of the problem. We've done all the simplifying, almost all of it, but we haven't rewritten the answer so that it only uses positive exponents. So how do we do that? What is the general principle by which we can turn a negative exponent into a positive one instead? What do we have to do? What's the trade-off? One of the ways to understand how to make a negative exponent into a positive exponent is to think about what it would take in this fraction to cancel out the u to the minus 13, for example, up here on the top. So if I wanted to cancel out u to the negative 13 from the numerator of this fraction, I should multiply the numerator of the fraction by something. But whatever I multiply the numerator of the fraction by, I also have to multiply the denominator of the fraction by. Otherwise, I'm going to change the value of the fraction. Right? One of our central principles behind working with fractions is if I multiply the top by it, I also have to multiply the bottom by it. So the question that I have then is, what can I multiply u to the negative 13 by to make it go away? It needs to be some number of powers of u, but how many? How many powers of u could I multiply u to the minus 13 by to make that minus 13 go away? Positive. Well, if I multiply by positive 1, then the total upstairs is going to give me u to the 1 plus negative 13. That's going to be u to the minus 12. So I still have 12 more negative powers of u upstairs. How about 13? If I multiply the numerator by 13 powers of u, then the total number of powers of u I'm going to have, according to the multiplication principle here, is going to be 13 plus negative 13, or 0. And so there will be no more u's left upstairs if I multiply by u to the power 13. And that's kind of what we want. But if I do it on top, I also have to do it on the bottom. And since there are no powers of u on the bottom to combine with this u to the 13th, what ends up happening is that I end up with a u to the 13th downstairs after my u to the u to the negative 13 upstairs disappeared. So here's what it looks like at the end of the day. V to the minus 3, w to the 2. Right? So multiplying this fraction by u to the 13th on the top and the bottom has completely killed off my u's upstairs, and instead it's just brought them downstairs. And this is the long version of what I usually describe as a shortcut. The shortcut being that to turn a negative exponent positive, that comes at the cost of switching multiplication for division. In other words, trading places in the fraction between numerator and denominator, or vice versa. So a negative exponent in one part of the fraction is the same thing as its opposite exponent in the other part of the fraction. U to the minus 13 upstairs is the same as u to the positive 13 downstairs. And this is a consideration that I like to worry about only at the very end of one of these kinds of problems. So after we've done all the other simplifying, then we worry about turning my negative exponents positive. And this is how we did it with the u's. What happens to v to the power minus 3?
Would it be the same thing?
Same deal. We can again think of it as just moving it from top to bottom, or if we want to be thorough, we can think about it as multiplying the top and the bottom by v to the power 3, which is going to kill off the v's upstairs because we're going to have 0 powers of v left, 3 plus negative 3, and it's going to introduce 3 powers of v downstairs alongside the 13 powers of u. And then I'll have no more v's left upstairs, but I'm still going to have 3 to the power minus 3, and I'm still going to have w to the power positive 2. And we're almost there. We just have one more negative exponent to resolve. What's going to happen to 3 to the power negative 3? The same thing. I'm going to multiply both top and bottom by 3 to the power positive 3. And again, you may not want to write this multiplication step every single time you do one of these problems, but I wanted to include it today just because I think it gives us yet another reason to practice our properties of fractions in working one of these problems. You can never have too many opportunities to practice fractions. And now all of the exponents that we have on the page are positive. Positive 2 exponent on the w, positive 3, 13, and 3 on respectively the 3, the u, and the v. There's only one more step that I want to do to finish this problem. What's the one thing that I still haven't simplified? 3 to the third. What is 3 to the third power? 27. 3 times 3 is 9, times 3 again is 27. And that will be how we finish simplifying for our final answer. W to the power 2 upstairs, and then downstairs 27. U to the 13th, V to the third. So we walked through this whole problem very carefully, step by step. Took us about 20 minutes to talk about every step. The more practice you get with these, the more that bits of it will start to become automatic. You won't take 20 minutes on every one of these probably. But the important part is that you're able to navigate your way through all the steps, all the different properties and the considerations that we have over on the left side of the screen. The last one, which I haven't finished writing down yet, is that any negative exponent that we have can be made positive just by trading places in the numerator versus the denominator. X to the minus n is the same thing as 1 over x to the n. So we can move from numerator to denominator or vice versa to turn a negative exponent into a positive one. And I've written the steps, I've written the properties the way that we've written them on the left-hand side of the screen, because that's the order in which I tend to like to consider these properties one at a time, following the guidance of the order of operations, worrying about parentheses and the distributive properties first, then worrying about taking powers of powers by multiplying the exponents, then worrying about multiplying and dividing powers by respectively adding and subtracting the exponents, and then only at the very end of the process, after everything else has worked its way through, then worry about changing your negative exponents into positive ones by trading places in your fraction.